Hello everybody! In my first video on the LFO+ADSR, implemented in Arduino and controlled through Ableton, I gave a demo and really focused on the usage. So I figured now it's time for a part 2, where we now focus on the installation and a bit of details on the code. As a reminder, what we're talking about here is an Arduino-based LFO+ADSR. You can see it on the right top. That is now controlled through Max for Live in Ableton. So I can change the shape, and as you can see, that real-time change over there. I can change the amplitude, and also I can enable an ADSR. Okay, so without further ado, let's go right to it. How do you install this program? Now, we have to first make sure that the LFO is working and that the ADSR is working. Not to extend this video too long, I have a separate video on the installation and the details around the LFO and the installation and details around the ADSR. Basically, you just need to unpack these libraries, rename the LFO to LFO, rename the ADSR to ADSR folders, and move those to the libraries folder of your Arduino. Here, we're going to focus on how do you program your Arduino and how do you install the Max for Live code. The link to GitHub, of course, is included in the comments below. So the first thing we do is, as always, download the zip file. We're opening the folder here. We'll have to unpack this. And you'll see that we get two folders, the Arduino code and the Max for Live code. The Arduino code should just be moved to wherever you have your Arduino files. In my case, this is in Documents and then Arduino. So that's where I put this. And the second file that we have is the Max for Live file. This one will need to be copied into Documents. Then we'll go into Ableton. Then we go into User Library. Then we go into Presets, MIDI Effects, Max MIDI Effects, and that's where that will need to be copied to. And that's it. Now we're ready to use the program. So how do you use it? Well, let's first start with programming the Arduino, and then we'll look into Max for Live. So the first thing we do is open up the Arduino Ableton LFO+ADSR. Of course, now I need to disconnect my serial connection from this plugin. Otherwise, it won't be able to connect. This INO file is right now optimized for the Arduino Duo. The reason I did that is that it's easy. It has a built-in DAC, so I can just set the analog write resolution to 12 and then write directly to the DAC port. If you want to use an ESP32 or an Arduino Uno, you of course can do that, but you will have to facilitate now a different DAC output. So either you put the DAC resolution to 8 bits, and of course don't forget to do that over here as well with the DAC size, or you write to an external DAC. If you do have an Arduino Duo, the only thing you need to do is just press upload. It will compile it and then upload it to the Arduino. And that's it. We can now switch to Ableton. So in Ableton, the only thing you need to do is locate the file we just copied there. That's in Max for Live, and then Max MIDI Effects, and drag it over to the MIDI track you want to control. And that's it. You're set up to go. So if I now open up the scope and press play, you'll hear it play the track. One thing I want to make you aware of is that the synchronization is set up such that it assumes you're at a full measure when you start playing a MIDI note. So if, for instance, you start here at measure 2, not a problem at all. The one thing is that if you start now in between measures, the LFO won't be synchronized until the next measure transition, and that will cause, in some cases, a glitch. So if I start here at a random location, then at the transition of 1 to 2, there's a bit of a glitch. Listen once more. Okay, obviously we don't really want that, but for me, I just got used to starting tracks in the beginning of the measure, and I'm not really annoyed by it. If you are, then it's relatively simple to, within the Max for Live code, provide the exact location of the phase where you're at when you do press play, so that the Arduino can synchronize to that. Okay, what is way more important for me though is that the latency is taken care of. We're controlling here a very old synthesizer, and that through MIDI, and that has quite an amount of latency to it when you press note on, and so we need to compensate for that. And in Ableton, if you use this external instrument to control synthesizers, there's conveniently a hardware latency section over here. So I'll show you now how to compensate for the hardware latency and how we deal with the LFO then later on. First, let's really only measure the hardware latency of the synthesizer itself. And of course, we want to then not have the LFO over-modulate, so I'll put the amplitude to 0 and just bypass basically the LFO. In order to measure now the exact latency that the synthesizer gives, I have a second track, an audio track, and that measures the audio output of my synthesizer track, track number 1. And if I press now record, then you see here in the beginning that there is latency. And if I zoom in all the way, this is about 23 milliseconds of latency. Perhaps it's a little tricky for you to see, but if I go over the mouse on the left bottom, this is about 23. That's it. So here, let me show you here on the monitor, 23 milliseconds. Okay, so we want to compensate for that, and we can do this by going to track number 1 and selecting in the hardware here 23 milliseconds. Done. If I now press record, then you see that the tone starts straight when the MIDI note is entered, because latency is compensated for. The problem arises when we now enable the LFO, because the LFO doesn't know about this hardware latency. So if I now put the amplitude up again and the offset down and I record, then I can show you that the LFO trace is not in sync. So you see that it is a little early, and I don't have to compute how much it is, because it's going to be 23 milliseconds. The reason for that is that, so we just measured that the MIDI, it takes from the time that the Ableton says note on to the time that the Jupiter 8 produces the audio signal, it takes 23 milliseconds. However, at the same time, when the Ableton would say synchronize to the Arduino synchronizes straight away and sends out the LFO waveform accordingly into the VCA. So the VCA is going to be about 23 milliseconds early, because that time from the Ableton to the VCA is really less than a millisecond. It's negligible. That's why, actually, I just discovered it while making this video. I was like, hey, why is this offset over here? I was like, of course, that's why. So I added a small little variable in the plugin to compensate for this latency. And we see that over here in the bottom, latency. And so you can go here and put that to 23 milliseconds as well. And if I now record, you see that it's pretty much in sync, maybe a half a millisecond optimization potential, but that's about it. So now that we're in sync, we can start to really use it. So here's a bit more elaborate track, just as introduction. The upper one is synth track, then there's bass line and some drums. Now below you can see the plugin that controls the LFO, and you can really use standard automation to now make changes. If I now enable automation here on the right, then you can select the plugin, and you'll see here all the parameters you can vary. So we have the sync port, then the DAC 0 and DAC 1, and in the bottom all the ADSR commands. If I take, for instance, the beat rate, you see that it varies a little bit, or the shape. There's all sorts of variations through the time. And the fun thing is, as with any automation, for the ones who are not that familiar with it, is that whenever you go now to a certain time in the track, the LFO will update automatically to what it is at that point in time. So if I click here on the track, then it will change to a sine wave. Or here it will change to ADSR, so that I need to press a trigger to see what happens at that point in time. Well, with that, you should be able to get started. But I would like to use a little bit more time to now show you what's behind the scenes and also how you can make some adjustments. I won't go through the basics again. There's a separate video about the LFO. There's a separate video about the ADSR. And there's a separate video about the communication, how to communicate between an Arduino and Ableton. So I refer to those videos for that. But there's a few things that also I discovered implementing this that I really would like to share with you. Okay, so there is a bug in Max for Live I really want you to know about. This is Max for Live 8.1.7, but I think it'll be there in 8.1.8 just as well. And that is that if you change many parameters and you write them all to the serial port, you overload it, and then Max for Live loads Ableton so heavily that the complete audio playback crashes. So while making the final edits for this video, I wasn't really sure if this came across really clear enough. So I decided just to add a few more slides for explanation. Now, when we change a parameter like you see over here, then it's a discrete change. The first blue arrow, that's where we have a first change from one value to another. And then the second blue arrow is where we change it back. So there's only two serial commands that will be sent from Ableton to the Arduino. It is completely different, however, in case of continuous or gradual shift or change. So I show that over here. And in this particular case, we have a starting point over here where we go all the way down to 0. And there's a continuous change from the starting point all the way to the end point, where we don't really define what the computer should send when, but we do define where it should end and at what time it should end. Now, what the computer should, of course, do is split this time up from the start point to the end point in reasonable amounts, and then periodically send an update to the Arduino. However, what Max for Live does is it wants to, every value, every small little step that it's changed, update the Arduino. So let's say from the start point to the end point, we're going over 10,000 points, then it wants to send 10,000 serial commands, which of course doesn't make a lot of sense. I hope this makes it a little clearer. So let's get back to the video. So emulate that over here. Not nice to listen to. If I actually just turn off the sound of the synthesizer, you can hear very clear that this is really Max for Live messing up Ableton. All right, took me a long time to figure it out, but it's actually relatively simple to solve. The first thing that I need to do is really increase the baud rate to the maximum, and what reliably worked was about 115 kilobytes for me, but play around with this. Maybe you can crank it up even further. The higher the better, obviously. The second thing that I did was I introduced a gator, meaning that whenever you do these continuous slides changes, do you really care if the amplitude changes every millisecond or less? Or is it fine if it's just every 5 milliseconds or so? And so that is the one here on the right. And also here, I need to interrupt myself for some additional explanation. What I really do with this metro function is the following. We basically split up this continuous change for Ableton. And that way, instead of having Ableton send every single command change in those 10,000 points, to take the example below, we just tell it to only look for changes every, say, 25 milliseconds or every 5 milliseconds or whatnot. And that's what we do with this metro command. So metro just generates a pulse sequence of bangs, and the number behind it is the number of milliseconds in between bangs. So you see here a metro 25 as an example that will give you 25 milliseconds between bangs. I think realistically for any song you'll be making, 5 milliseconds should work just fine. I have most of the time the metro at 2 or 5 milliseconds, and that works great. One thing to note, in the video, I kind of point to this 1 on the top first. That one is only needed to make sure that the metro also really outputs bangs. If I would leave it out, then metro doesn't work. So don't be distracted by the big 1 on the top. It's the metro 25 you want to play around with. Okay, back to the video. So I set the value here on metro 1, and this, of course, is a very, very low value. That's why we hear these glitches. How high should you make it? You don't want to make this too high, because if you make it 100 milliseconds, then only once every 100 milliseconds you'll get changes to your envelope, which is definitely something you'll be hearing. Now, in this very extreme case where I change all the parameters at the same time, I needed about 25 milliseconds to really get it to run. But under practical circumstances where you may be varying 1 or 2, you can really go down to 10 milliseconds or 5 milliseconds even over here. So then, and obviously if you don't do these gradual changes, you don't really need to care about this at all. You can just leave it at 1. So let's have a listen now with 25 in it. If we go back here, let's play the same thing. So, as you can see, now it plays without a problem. But if you hear this in your track, you should straight away think about, okay, this is the synchronization. This is really the Max for Live trying to send too many serial commands to that Arduino. And you know now where to go to fix it. Here you can see as well what all changes: continuous sweeps of attack, decay, sustain, release, offset, and phase of the other DACs. And so that's lots of data for the serial port. Normally, I guess you won't be doing that, but if you plan to do that, then you need to take this into account. Okay, so that's basically it for the Max for Live environment, but there's also a part of it in the Arduino code, and that's something I would like to discuss with you as well. So let's open up the Arduino code. Okay, so we start from the top. Yeah, so initially we just get our classes on board, define a DAC size, etc., the standard stuff. Now, where it becomes interesting is over here. In this section, we define the control numbers, how we interface with Ableton. So as a quick reminder from my other video on this communication, we have a 4-byte communication where the first one is just a synchronization byte, 255, but then there's a control byte that defines, am I now trying to set the attack, the decay, or am I trying to set the DAC 0 rate or whatever. And then byte 3 and 4 are the actual value that we want to set. 2 bytes because it's a 16-bit value, so we split it up into 2 bytes. Now, the list that we see over here, starting from ID song measure all the way down to ID DAC 1 ADSR enable, those are the definitions of the control values. So, for instance, if we do receive a control value 251, then this is the ID song measure. So that means that we'll be sending the ID, are we now in measure 1, measure 2, measure 3, etc. And that way the communication is realized. As said, refer to my dedicated video on the communication for more information on that. So continuing here on the pin assignments, there's a few pins that I address. Of course, we have the DACs, but I don't need to assign those pins because they're hardwired on the Arduino Duo. But in addition, I have a sync output. This generates an LFO value with just 0 to 1s so that you can synchronize external LFOs. And so I put that to port number 43. Then there are 3 LEDs here, LED DAC 0, DAC 1, and sync. Those are just additional ports where I just put on some LEDs so that you can see the rate that they're going at. And then finally the LED measure. This LED goes on and off with every measure that goes by when you hit play on Ableton. There is actually also the LED number 13. I use that for debugging. Whenever serial commands are received, that LED goes on for half a second. Now, there's a couple variables here. I won't go into the details too much. So let's maybe just skip down to the setup section. It's pretty straightforward. We set up our classes, we set up our pins. But very important here, serial command begin. This is where you can play around with the serial speed. And of course, you need to match that with the serial speed here in Max for Live as well. That's over here, serial A 115200. And then basically we start with the main loop. Now, in the loop, we take the current time. We then update DAC 0, we update DAC 1, then we update the sync port. This is a small update for the LED that identifies the serial port. And then here, the bulk of it really is where we are handling the serial commands from Ableton. So we receive the serial commands here, first the synchronization byte, then the control byte, and then the value byte in 2 pieces. So once we receive the second piece, we need to put them together again. So here you see a value that is basically the combined most significant byte and least significant byte. Now we have all the parameters, and we can update the parameter that is to be updated. So here in these if statements, we just go through the individual control numbers and update the specific parameters depending on what has been received. Let's take an example. If we see here that CC control is equal to the ID DAC 0 mode, then we just call the class of DAC 0 and update the mode to that particular value received. Now, there is one thing to consider, and that is it's only possible to send integers between Ableton and the Arduino. And of course, some parameters, they are decimal parameters. For instance, if you want to be able to set the BPM to 120.4, this would not be possible if we can only send integers. And so for those, I do a small little translation. BPM, for instance, I multiply in Ableton the BPM with 10. And then when receiving the BPM here, I divide it by 10 again so that you can set 120.4 as well if you need to. Similarly, let me just give you a couple other examples. We have, for instance, the attack time of the ADSR. The attack time is normally set in microseconds, but if I were to do this in microseconds, I couldn't do that in 16 bits because 16 bits only gets you up to 64,000 points. But if we were to really send the information in microseconds, we would need something like 40 million points. And I don't want to waste those many bytes. Besides, there's no real use to set an attack in microseconds accuracy. So that's why in Ableton, I send out the attack time in milliseconds. And here I need to now multiply it with 1,000 to convert it to microseconds. Another example would be the phase. So any phase is sent from 0 to 359. just going for the 360 degrees. That's more logical, I guess. And then I convert that here to a value from 0 to 1. Okay, whenever I did a conversion, I added that as a comment here in this particular section. So I hope that is understandable for you. And if not, just post me a question. Happy to comment to it. So the last portion I would like to discuss in a little bit more detail is how we update the DACs. Now, let me briefly go to that section. Here we update DAC 0. And that code's a little bit more complex than the code that we had for just the LFO or just the ADSR. The shape of the ADSR and the LFO is computed 100% in the class, so that's not shown here. But the thing is, we have an LFO shape and we have an ADSR shape. And how do we want to combine the two? And for me, I let it depend a little bit on the mode we're in. So I'd like to demo that to you briefly, and then we'll look at the code implementation as well. So in Ableton right now, I enabled the DAC 0, and we're going to look at the scope. Let me make the scope a little bigger that you guys can see more clearly. I'm just going to manually trigger MIDI notes. In this setup, the LFO is modulating. I have it on sawtooth, but it doesn't really matter if it's saw or triangle or square. If I now trigger, then you see that we get an overmodulation of the amplitude. And I just like that behavior quite a lot. But you can change this. I'll show you briefly in the code later on. If I now put it on a DC value and I do an ADSR, then we get the typical ADSR shape and it just goes up. Okay, so that is why the DAC section is a little bit different for the DC mode and for the modulated LFO mode. So let's now have a look in the code as well. In this first section over here, we just see for DAC 0 if the ADSR is enabled. If it's not enabled, well, we don't need to care about it and we can just write the LFO to the DAC. Then here, if the ADSR is enabled, we briefly check if it's DC. And if it's DC, then the LFO will just basically return amplitude offset. And what we then do is we take that amplitude offset and then overmodulate the ADSR to the maximum that the DAC can do. So that's what you see here, this map, ADSR get wave, and then the ADSR, of course, spans from 0 to the DAC size, and we need to translate this to the amplitude offset that the LFO has to the DAC size. And so if the LFO is actually modulating, so it's not DC, then what we do is that we write the ADSR shape to the amplitude of the LFO class. So we have here a function DAC 0 LFO set amplitude. And of course we need to map now the ADSR. We can't always map it to the full DAC size. We need to map it to the DAC amplitude that it was actually set at. So here we map the ADSR range from 0 to DAC 0 amplitude. And this DAC 0 amplitude is a local variable within this program that I defined in the beginning to keep track of what the actual amplitude is. Otherwise, if we would write the amplitude to the class, then the class doesn't know anymore what the original amplitude was. And then finally, there's one statement here that writes to the LED that correlates to DAC 0, so that in the begin phase from 0 to 0.5, the LED goes on, and in the second phase, the LED goes off. So it blinks according to the LFO rate. And that basically is the copy-paste for DAC 1 as well. If you want now the LFO to behave differently, so if you want to combine the LFO and the ADSR in a different way, then this would be the section where you can change it to your liking. Okay, that's about it. Hope you liked it. As usual, leave comments down below. Likes are well appreciated, and see you in the next video.